So many things in our world actually goes through simple harmonic motion. Three easy examples that we can talk about right now are pendulums swinging back and forth, springs bouncing up and down, even wheels going around, where we look at one of the components, the x component, let's say, of an object on the rim as it goes around executing simple harmonic motion. And there are so many more that we're going to talk about, especially in the resonance section. Now, simple harmonic motion is an oscillating motion where the acceleration is always pointing back towards equilibrium. Now, equilibrium is the spot where everything's at rest. That's the position of object. All forces and torques are balanced, the center position, or if you left it alone, that position. But the acceleration is always back towards equilibrium, and it's proportional to the displacement away. So the further away you get, the greater the acceleration, meaning at the amplitudes, the furthest extent away, you're going to have your maximum acceleration. And at equilibrium, by definition, position of an object where all forces and torques are balanced, meaning that you would have zero acceleration here. Now, the defining equation for simple harmonic motion is acceleration equals negative omega, that's your angular velocity, squared, or your angular frequency, squared, times the displacement away. In differential form, remember acceleration is the second derivative of position, so d squared x dt squared equals negative omega squared x. Now, about this, there are a few very important things to recognize here. Notice first that the acceleration and the displacement are proportional. Whenever your displacement goes up, you get further away from equilibrium, you get a larger acceleration. And one of the most important things about this equation is this negative sign right here. It's always pointing back towards equilibrium. In other words, if I declare to the right positive and to the left negative, whenever our displacement is positive, so the pendulum bob is on this side, so we have a positive x, acceleration, positive times a negative, acceleration is negative, pointing back that way, which is what should be happening. The pendulum is always trying to pull the bob back towards equilibrium, and vice versa. If our displacement is negative, so we're on this side of the pendulum, so we're over in the negative side, the acceleration, negative times a negative, a positive, the acceleration points back positive, trying to return it back to equilibrium. Now, before we launch into an example problem, let me remind you of some basic things here. Period equals 1 over the frequency, and your angular frequency, same thing as angular speed, 2 pi f, or 2 pi divided by the period. Now, pendulum inside Big Ben, very famous clock, quite obviously, in London, completes a cycle every 2 seconds. What is the acceleration of the pendulum at its amplitude whenever it's furthest away? And we're going to give amplitude here in actual linear distance, 15 centimeters away from our 0 point, our equilibrium. A lot of times we're going to give amplitude for pendulums in terms of angle. More to come on that in a little bit. Now, whenever I write my acceleration equation down, I'm looking for A. I do know x, 15 centimeters, the amplitude. That's the displacement away in this case because we're looking for it at the amplitude, so displacement at the 0.15 meters. The problem is I don't know my angular frequency, but I do know my period, completes a cycle every 2 seconds, and I have an equation for omega coming from period. Now, if you would like, you could work this through solving for omega in numbers and then substituting in and working all this in numbers. I'm going to purposefully work this in letters, so I'm going to go ahead and substitute my 2 pi over period in for omega. Also of note in this equation, this negative sign is out in front. It's omega squared times then the negative, but you do the squared first. That negative sign is not attached to the variable. And with the two sig figs that I'm given, I come out with 1.5 meters per second squared, negative 1.5 meters per second squared. I use the positive amplitude. I use positive 15 centimeters here. Because of that, the acceleration must be going back the other way, the point of the negative sign to bring it back to equilibrium, negative 1.5 meters per second squared. Now remember that acceleration is actually the second derivative of position, and so this equation is actually a differential equation. Now we're not going to actually worry about solving that through. You don't have the math skills just yet. Don't worry, you will get there. But instead I'm going to tell you what the solution to this differential equation is. It's x equals your x naught, or your amplitude, or the maximum displacement would be another way to say that, cosine omega t plus phi. So it's a cosine. You could also do this with sines, but we're going to purposefully use use cosines. The reason we're going to use cosines is because so often, whenever you're trying to start something in simple harmonic motion, you pull it back to its maximum displacement or its amplitude. And check out the cosine graph. This is a cosine graph. It starts out at t equals 0 at its amplitude, which is what you generally do. If you're going to start a pendulum in motion, you pull it back to its highest point. If you're going to start a spring in motion, you pull it down to its furthest point or you push it up to its furthest point. Now let's actually label this cosine graph. You've gone through these things in math before, but let's actually point that back out. Here is your amplitude is the maximum height or the maximum depth. Depth would be another way to look at it. The furthest away from equilibrium, where your equilibrium position is the x-axis here, where our x-axis has time in seconds on it, and our y-axis has the displacement away from equilibrium. How far away does it get? So here's your x0, or your amplitude, the maximum displacement, and here is the period, the time it takes to go through one oscillation. Now your brain should already be kind of thinking, okay, here's the period, I can use that to get my omega. Now, the solutions to this differential equation are here. Make sure you get these two equations down. X equals x0 cosine omega t plus phi, where phi is the phase shift. Phase shift simply means how far you slide this graph. So if we wanted to start it further this way or further that way, if we added on, let's say, pi over 2, everything would slide that way. If we subtracted pi over 2 here, everything would slide back the other way. Phase shifts are going to become very, very important later on in physics whenever we're talking about superposition of waves. So from the solution here, this differential equation, you have two equations. You have an equation that describes the displacement away from equilibrium, how far away it is according to time, right? All these others are constants. The only variable is time. And you also have a velocity equation, how fast it's going at any point. Here's your maximum velocity, right? Your angular velocity, t, or your angular frequency, time, phi. A lot of times we won't end up using phi, but I do need to go through and actually prove to you, backwards working if you will, prove that these are solutions to this differential equation. So let's start here and then let's take the derivative of our position equation, knowing that should get me to velocity. Now looking at this derivative, this is a constant, and then we have cosine of some stuff inside. And the stuff inside here is my variable. This is a constant also, so I have a constant times a variable here. Now, the derivative of cosine is negative sine, and what we're going to have to use here in a second, the derivative of sine is cosine here. So whenever I'm taking this derivative, the constant out in front of this is going to remain there. But then I need to take the derivative of my cosine, and the derivative of cosine is negative sine with all that stuff in the middle. But I'm not done yet. There's something called chain rule. Chain rule says that whenever you take the derivative of something that has parentheses, something that's, if you will, encapsulating another thing, you must also take the derivative of the inside and multiply it back on the outside. That's just a calculus principle. If you're unfamiliar with it, don't worry, we'll go over it. But here, I need to take the derivative of the inside. Now, this is a constant times t plus a constant. So the derivative of a constant times my variable is just the constant. So I need to multiply an omega out on the outside. And the derivative of a constant is 0, so I don't need that there. I'm going to rearrange this equation, putting the negative out in front and sliding the omega out in front as well. Now, if you remember back to the previous unit here, omega times delta x looks awfully familiar. In fact, that's the idea of linear velocity. How do we get from angular velocity to linear velocity? Well, we multiply by the radius. Here is the radius, or the distance away from equilibrium. Let's actually write that out to the side. Your maximum velocity is going to equal your angular frequency times your maximum displacement. This is v0. And so this equation is that equation, just simply taking the derivative. The velocity at any point in time is negative the maximum velocity times sine omega t plus phi. Now let's take the derivative again, aka we're getting to the second derivative, right? And the derivative of velocity is acceleration. The second derivative of displacement is acceleration. Now taking the derivative again, I'm going to have to use the same principles I did before. These two out in front are constants, so they get to remain there exactly the same because I have a constant times my function here, sine of everything else. Here is my variable, sine of t. Now the derivative of sine is cosine. So this is going to end up becoming cosine omega t plus phi. And I left the negative sign there because the negative was part of it. And notice, though, that it does not change back to positive. Derivative of cosine, positive, or derivative of positive sine is positive cosine. The only one that switches sign is whenever you take the derivative of cosine. Then it changes into a negative. I do also still need to use chain rule here. I took the derivative of the constant out in front. It stays the same, right? Constant times something. Derivative of sine changes the cosine, but look at the insides again. Once again, we have a constant times t plus a constant. Now the constant doesn't matter, derivative of constant is 0, but constant times t is the constant. So I need to multiply an omega out. And then let's rearrange. So combining my omegas here, I have omega times omega. That becomes omega squared. The negative still remains, right? So now I have negative omega squared x naught cosine omega t plus phi. Well, check this out. X naught cosine omega t plus phi, I already know. That is what my position equation is. X is x naught cosine omega t plus phi. We ended up coming back around to it. So this entire thing is x. The second derivative of position is acceleration, so I end up a equals negative omega squared x, proving that this is actually here, this is the solution to our differential equation because we took the derivative of it twice to get back to what our differential equation is. Things you have to remember from this. You are required to know the proof to actually be able to go through to show that the solution to our differential equation is x equals x naught cosine omega t. Other things, please make sure you remember what the solutions are for position and velocity, and it would be good to remember the maximum velocity equation. Before we work this example problem here, let's go back and let's examine when my acceleration velocities are maximum and 0. At our amplitudes, at our maximum displacement, we have maximum acceleration force trying to pull it back towards equilibrium. But we are at rest at the amplitudes because it comes up and then it pauses for just a second, right, to come back down. It's not a literal pause, but you do have to, the velocity does reach 0 at the amplitudes. Now at equilibrium, we have 0 acceleration, but that's where my velocity is maximum because we have converted all this energy, that's kind of alluding to something coming in the future. We've converted all of this potential energy back into kinetic, speeding up as we come through the equilibrium position, but then we start to lose energy, right, or lose kinetic energy, converting it to potential, slowing down as we come back up to the amplitude. All right, so now, number one, using this graph here that's describing the simple harmonic motion of an object, maybe a pendulum here, or a spring, or something else that's vibrating back and forth, sketch a velocity time graph of it. Now, first thing that we need to see is that our period is pi. So our graph needs to go through one oscillation between 0 and pi seconds. Second thing we need to realize is we do not know what the maximum velocity is. I do know what the amplitude is. The amplitude is 3.5 centimeters, it says. So we're going to stretch up and down whatever the maximum velocity, not 3.5 centimeters. I need to stretch up and down at some other distance. Now remember that the maximum velocity equals your angular frequency, angular speed, times your maximum displacement. Now, I know my displacement, 3.5 centimeters. I'm actually going to change my unit here for velocity to centimeters per second so that we don't end up having to convert. I just need to know omega, and I don't know omega, but from this graph, I do know the period. Pi seconds, and I have an equation for omega, right, from period. That's going to be 2 pi over the period is my omega, so I can substitute that in. So as you can see, I'm going to oscillate between, in my velocity graph, 7.0 centimeters per second and negative 7.0. Those are going to be my amplitudes. Now I need to actually translate the graph over. Remember, at the amplitude, the velocity is 0. So the first point I'm going to put here is at the 0, because at the amplitude, right, whenever the displacement at t equals 0, I'm at my amplitude, so my velocity should be 0. And whenever we hit equilibrium, my velocity is at a maximum. But check out the slope of this line. Which way is it going? Well, here it's going down negative, right? The slope of this line is negative at that point, meaning slope of the displacement time graph is velocity. My next point should be down at -7, maximum velocity here. Then we come back up, right? We come back down. This is the negative amplitude, but velocity at the amplitude is 0, so at pi over 2. I'm back at 0. Then we come back up, right? And whenever we pass through equilibrium, at equilibrium, velocity is maximum. Check out the slope. We are on the way back up, meaning we have a positive velocity. So at 3 pi over 4, halfway between pi over 2 and pi, I'm up here at +7. And then whenever we finally reach pi, the end of the cycle here, we are at, once again, our amplitude, and velocity is 0 at my amplitude. Now we're going to connect the dots. And whenever you go through the connecting of the dots and that, making sure that we're all smooth, you can see that we have a beautiful negative sine graph, which is exactly what we expected. This is a positive cosine graph, so the velocity graph should be negative sine. Now, number 2 is relatively easy. It's asking for the maximum acceleration, and you need to remember maximum acceleration happens at the amplitude, 3.5 centimeters here, and so I'm going to end up with my acceleration in terms of centimeters per second squared. I do not know the angular frequency here, but I do know an equation for angular frequency, and off the graph I'm able to get the period. Substituting in the equation for angular frequency in terms of period. In this case, again, the pi's can cancel out, maybe making what I type into the calculator a little bit easier. And I come out with a maximum acceleration equal to negative 14 centimeters per second squared. That's, of course, happening at the amplitude, in this case, happening at the positive amplitude up here. If it were at the negative amplitude, this would be a positive. So positive or negative 14 centimeters per second squared would be acceptable.